Welcome to the lecture module on optics. We are now discussing wave optics. In the last lecture, we discussed the Huygens principle. Christian Huygens introduced the wave picture for light propagation. However, as we have seen, although he could explain the reflection and refraction of light at interfaces, there were certain questions which he did not have answer, or Huygens wave theory did not have answer. But as we discussed that in 1801 Thomas Young presented the Young's interference experiment, which was a convincing proof that light is a wave. So, today we will discuss the Young's experiment in some more detail. So, Young's experiment, Young's interference experiment. First of all, interference in optics, generally interference refers to two beam or two wave interference, which result in some perceptible and sustained fringe pattern. We will discuss about the fringe pattern, what is this fringe pattern in the later part of the lecture. So, we generally refer to two beam or two wave interference, which results in a perceptible and sustained fringe pattern. A fringe pattern refers to the light intensity pattern comprising of alternate bright and dark regions in the form of lines or rings. For example, let me show a typical fringe pattern. So, here is a fringe pattern which is a linear fringe pattern. So, this is the kind of pattern which we would get in a Young's experiment, or it could also be a circular fringe pattern. These are of course computer generated fringes. So, it could be a circular fringe pattern as in the case of Newton's rings, and we will discuss the formation of these fringes in the next few minutes. And formation of fringes can be explained in terms of superposition of the two waves. So, first let us look at, there are certain requirements although to get a certain sustained fringe pattern, and let us look at the requirements to obtain a sustained fringe pattern. So, here the requirements of interference. What are the requirements of interference? To be able to see a sustained fringe pattern, the two waves interfering must have the same frequency or wavelength, and there should be a constant phase difference between the two waves. This property is called coherence. The two waves must be coherent. So, there should be a constant phase difference between the two waves. We will discuss these issues towards the end of the lecture or in the subsequent lecture and understand this more clearly. So, let us come back to the Young's schematic of the Young's experimental setup. So, here is the Young's experimental setup. So, first we see here that the experimental setup comprises of a source. There is a small hole in this, there is an opaque screen in which there is a small hole or a aperture, and then there is a second screen, there is a second plate or screen or a cardboard where you have two small holes S1 and S2, two small apertures. So, that is why it is called Young's two hole experiment. So, there are two holes which act like point sources, and then we have a screen here on which the interference pattern will be observed. So, we will discuss the formation of interference pattern. So, the coordinate system that we consider is the z axis, light is propagating in the z axis here. So, this is the z axis, and the obstacles here or the apertures here are on a plane which is perpendicular to the z axis, and the screen is in the xy axis here. So, xy axis, the xy plane lies on the screen. So, this is the experimental arrangement. Now, if we see a longitudinal cross section along the xz plane. So, xz plane. So, this is the x and this is the z direction. So, if we see a longitudinal cross section of the xz plane, it would look like this. So, here it is. So, the source is here. So, we are looking at a cross section. So, source S is shown here. There is a small hole which acts like a point source from which spherical wave fronts are emerging. Then there are two other small holes which act like point sources again. So, the spherical wave reaches here, and as we know from the Huygens principle that each point on the wave acts as secondary source of secondary wavelets. So, these 2 points or these 2 small apertures act like point sources, and here is the screen. So, again it is shown here that the x axis is here, and we have shown a cross section, a longitudinal cross section. The separation between the 2 holes here and the screen is capital D, and the aperture, the separation between the 2 holes here is small d. And at any point P, the resultant intensity can be determined by considering the superposition of waves. Superposition of waves occur at each point on the screen, at each point. First, we will consider the superposition of waves on the x axis, and then we will take a general point, an arbitrary point anywhere on the screen. So, first a point P is a point, an arbitrary point on the x axis here, on the x axis. So, superposition of waves occur at each point P, and d is the distance between the source S1 and S2. S1, S1, S2 are small holes in an opaque screen. Okay. So, we will now discuss the superposition of waves to determine the interference pattern. So, let us look at the superposition of waves here. So, at an arbitrary point P, these are the 2 point sources S1 and S2. At a point P here, which the distance is R1, from S1P is R1 and S2P is R2, and we can see that the point source S1 can be represented by psi 1 equal to the disturbance due to S1, the wave due to S1 at the point P can be written as A1 dash by R1 cos k R1 minus omega t, and due to the point source at S2, psi 2 is equal to A2 dash by R2 cos k R2 omega t. If we denote this A1 dash by R1 as A1 and A2 dash R2 by R2 as A2, then we have the resultant at the point P is the superposition, which means we sum it psi 1 plus psi 2. Psi resultant at the point P is equal to psi 1 plus psi 2. So, that is A1 cos k R1 omega minus omega t plus A2 cos k R2 minus omega t, which can be opened up. So, now we can open cos A minus B is equal to cos A cos B plus sin A sin B, we can use that formula, and so therefore, we have this term has cos k R1 cos omega t plus sin k R1 sin omega t, and the second term A2 is equal to cos k R2 cos omega t plus sin k R2 sin omega t using the trigonometric identity. Now, the superposition of 2 waves. So, let us calculate the resultant due to these 2 waves. So, let me continue with the resultant, calculation of the resultant. So, the psi resultant is equal to cos omega t. So, we have taken cos terms which are common. So, in this expression here we had cos omega t here and cos omega t here. So, we are taking common terms and sin omega t and sin omega t here. So, this can be written as cos omega t into A1 cos k R1 plus A2 cos k R2 plus sin omega t into A1 sin k R1 plus A2 sin k R2. Now, we set A1 cos k R1 plus A2 cos k R2, that is this term here, as A cos phi, and A1 sin k R1 plus A2 sin k R2 as A sin phi, where phi is given by the phi, the angle phi, such that this holds good, is given by tan phi is equal to A1 sin k R1, that is we simply divide this by this, we see that dividing the second equation by the first equation, we get tan phi is equal to a1 sin k r1 plus a2 sin k r2 divided by a1 cos k r1 plus a2 cos k r2. And therefore, the resultant psi now, so this term is a cos phi and this term is a sin phi. So, the resultant is a cos omega t cos phi plus a sin omega t sin phi. In other words, that is nothing but psi resultant is equal to a cos omega t minus phi at the point P. Now, with a is equal to a square cos square phi plus a square sin square phi. Why we have to the power half? Why we have written this? Because a will come from this, a will be determined from this square of this and square of this and square root a square cos square phi plus. So, that is given by a is given by this and phi is determined by this equation. So, we have the resultant disturbance or resultant function or the resultant wave at the point P as a cos omega t minus phi. Let us find out what would be the corresponding intensity distribution. So, the intensity distribution is given by mod psi square and therefore, we write that the intensity at the point P is equal to, so intensity at the point P is equal to mod psi resultant square, which is equal to a square cos square omega t minus phi. Now, cos square omega t minus phi, because omega is a very large number. So, we are determining the intensity, omega is a very large number. So, what is omega? So, let us just discuss this here. So, omega is equal to 2 pi into nu, where nu is the frequency of light corresponding to light. So, nu is typically of the order of 10 power 14 to 10 power 15 hertz for light, depending on whether we are at the blue end or whether we are at the red end. So, this is a very large frequency and therefore, cos omega t, so cos square. So, we have cos square omega t minus phi. So, this is what we have to determine. This quantity is varying extremely rapidly with time. So, we have a cos square function. So, cos square we know varies from 0 to 1, cos square it is, therefore, it varies from 0 to 1. This is time axis. So, with the time this is varying extremely rapidly, very rapidly, and this time difference here is of the order of 10 power minus 15 seconds, because the frequency is of the order of 10 power 15 hertz, which means the corresponding period is 2 pi by t, which is t is equal to 2 pi by f, the frequency, and that is of the order of 10 power minus 15 second, which is extremely rapidly varying. So, neither I nor any high speed detector can detect such high frequency variations, and therefore, what we will detect is an average value. That is why we take an average value. This has been probably discussed in an earlier chapter, that cos square omega t minus phi is a rapidly varying function. So, whenever we determine the intensity, the rapidly varying function has to be average. So, these brackets refer to time average, time average. So, the time average is equal to half, because the maximum is 1, minimum is 0, it is varying rapidly between 1 and 0, and therefore, on an average we see that the function varies, the value of this cos square omega t time average is half. Using this, we come back to the superposition of waves. So, we get the intensity variation here is cos square omega t time average using this equal to half. We have I is equal to a square by 2 a square into half. So, a square by 2. If only the source S1 was present, for example, so if we had, so this is resultant due to both the sources S1 and S2. If only the source S1 was present, let us say S2 was not there, then we would have got intensity at the point P equal to mod psi 1 square, which is equal to, here of course, we have taken all real quantities. So, we even need not write mod. So, A1 square into cos square k r1 minus omega t, because there is only one source. So, k r1 minus omega t gives us the phase term, and therefore, we will get A1 square by 2. The intensity due to source S1 is A1 square by 2, and similarly intensity at point P due to only S2, that is if S1 were not there, then we would get I2 is equal to A2 square by 2. Now, let us continue further and see what is the resultant therefore. So, the resultant here now is A square is equal to, remember we had written A square cos square plus A square sin square. So, this is A cos phi, and therefore, A square is equal to this square plus this square. So, recall the expression we had written here. So, A is equal to A square cos square phi plus A square sin square phi, where A cos phi was this term and A sin phi was this term. So, now we are using this to determine A. So, A square is equal to square of this, and therefore, A square is equal to square of this plus square of this, which gives A1 square plus A2 square. So, we can square and add them. This gives cos square k r1, this gives sin square k r1, A1 square. Therefore, we will get one term as A1 square, another term as A2 square, and the term, the mixed term as 2 A1 A2 cos k r1 minus k r2. That is 2I A square, we have just now shown that A square is equal to 2I. So, we have just now shown that I is equal to A square by 2, or A square is equal to 2I. So, A square is equal to 2I is equal to 2I1 plus 2I2 plus 2 times A1 is square root of 2I1 into A2 is square root of 2I2 into cos delta. We are calling this as delta, where delta is equal to k r2 minus r1, that is the phase difference between the two waves at P. This is the phase difference between the two waves, because omega t is common. So, we had one wave with cos k omega t minus k r1 and the other term with cos omega t minus k r2. Therefore, the phase difference is k r1 minus k r2. Delta is equal to k r2 minus r1 is the phase difference between the two waves interfering at the point P. Now, r2 minus r1 is the path difference. R2 is this distance S2P, r1 is this distance. Therefore, r2 minus r1 is the path difference between the two waves. Path difference multiplied by the phase constant gives us the phase difference delta. Therefore, using this as delta, we have, so 2 cancels throughout, we have I is equal to I1 plus I2 plus 2 root I1 root I2 cos delta. This is called the interference equation, the interference equation. Now, we will determine the intensity distribution as a function of delta. Delta depends on R2 minus R1, which means at different positions P on the x axis, we will have different path differences and therefore, different phase differences and therefore, different intensities. So, we will determine the intensity distribution along the x axis. So, the intensity distribution here on the screen here on the x axis is given by, so here we are. So, this is the interference equation. For delta is equal to 0, plus minus 2 pi, plus minus 4 pi, etc., directly looking at the mathematical formula here. So, delta is equal to this, we have I is equal to I max, because this cos delta is 1 and therefore, this term is simply square root of I 1 plus I 2 the whole square, I max. And for delta is equal to plus minus pi, plus minus 3 pi and so on, we will get I is equal to, we will get a negative sign here, cos delta being minus 1, and therefore, we have I will be equal to minimum, which is equal to square root of I 1 minus I 2 minus square root of I 2 the whole square. So, this is the maximum intensity and minimum intensity depending on the value of delta, which as we see that it will depend on the position of the point P, because delta will take different values depending on the position of the point P. And therefore, if A1 is equal to A2, as is the case here, we can see that S1 and S2 are drawn from the same wavefront. If we look at the, if we recall the diagram here, that S1 and S2 are drawn from the same wavefront and therefore, they have the same amplitude and they are in phase at this point. We will discuss more about the phase and phase differences in a later lecture. A1 is equal to A2 and therefore, I1 is equal to I2 is equal to I0, let us call it as I0, then I max will be equal to 4 times I0, because this will be I0, this will be I0. So, it will be 2 times square root of I0 square gives us 4 times I0, for delta is equal to 0 plus minus 2 pi and so on. And I minimum, I1 is equal to I2, therefore, I minimum will be equal to 0. And the I, the intensity here given by this, for the case of I1 is equal to I2, that is A1 is equal to A2, will be I is equal to 2 I0 into 1 plus cos delta here, 1 plus cos delta, and this can be written as 4 I0 cos square delta by 2. So, the intensity distribution on the x axis depending on delta will be given by this expression 4 I0 cos square delta by 2. So, we can see how does the intensity vary. So, we can plot intensity as a function of delta. So, if we plot the intensity variation as a function of delta here, so it is shown here I of delta is equal to 4 I0 cos square delta by 2 and delta here is given by, so let us look at the diagram first. So, delta is equal to k times R2 minus R1 and for this is delta versus intensity. We can see that whenever it becomes an integral multiple of 2 pi, intensity becomes maximum, and whenever it is an integral multiple, that is odd integral multiple of pi such as minus pi, minus 3 pi, pi, 3 pi, we have the intensity going to minima. So, this is the intensity variation as a function of delta. Now, delta is equal to this, therefore, k being constant, k is 2 pi by lambda, therefore, it is the path difference which will determine the intensity distribution. So, let us calculate the path difference. For a point P on the x axis here, R2 minus R1 is nothing but S2P minus S1P, S2P minus S1P. So, if we see the coordinates here, S2P, so this hypotenuse of this right angle triangle. So, S2P square is equal to d square plus this square. This is x coordinate x plus this small difference here. So, this is d by 2 because d is the separation between this and therefore, half of it. So, O is on the perpendicular bisector between this S1 and S2, therefore, each one is a half here. So, d by 2 as shown here, d by 2 and d by 2. So, we have S2P square is equal to d square plus x plus d by 2 square and S1P square is equal to same d square plus x minus d by 2 square. And therefore, S2P square minus S1P square is simply equal to 2xd, or S2P minus S1P is equal to 2 x d divided by S 2 p plus S 1 p. We have not made any approximation so far. So, there is no approximation and we have got the expression for path difference. So, we will discuss how the path difference determines the intensity, but let us have a look at the practical situation now. So, the path difference here R 2 minus R 1 is 2 x d by S 1 p plus S 2 p. In a practical setup, one can determine this accurately, but in a practical setup we want to make a practical approximation. Typically the d, the separation between the source plane and the screen here is 50 to 100 centimeter when we do experiments in a lab, and the separation between S 1 and S 2, the two holes here are separated by a very small separation, typically between 0.1 and 1 mm. We will see some numericals and we will see that this d is generally about 0.3 mm, 0.4 mm and so on. So, we want to get a feel for the numbers now. So, the separation is of this order, d is much larger. So, this is 500 to 1000 millimeter and this is d is very small, and the screen on which we see here is typically few millimeters to few centimeter distance only where the fringes are formed, and because of various reasons as we will discuss a little later, and therefore, I have deliberately drawn this setup to get a feel. Earlier we have discussed showing this setup. Now, I have tried to show in a real scale, although this is not exactly to scale, d is much larger compared to d, and the x, the point p that we are the position of the point p is also much smaller compared to d. So, noting that x comma d are much smaller than this, then we can write S 1 p plus S 2 p, that is S 1 p here and S 2 p here as 2 times d. We are approximating S 1 p equal to d and S 2 p equal to d. This is an approximation, but it is a very good approximation. Later on we will see that if we put some numbers, the error that we will make is extremely small, much smaller than 0.01% or so, and therefore, this is a very good approximation in practice. And using this approximation, therefore, we can write the path difference R 2 minus R 1. So, we are substituting 2 d for this, 2 capital D is equal to x d by d. In other words, the path difference R 2 minus R 1 is proportional to x, the position coordinate of p here. P is a point on the x axis, and we have already seen that the phase difference is proportional to R 2 minus R 1, because delta is equal to k into R 2 minus R 1. Now, let us see what is the corresponding fringe pattern. How would we see the intensity distribution? We are determining the intensity distribution and through estimation of the path difference, and therefore, the intensity maxima and minima are now given by. So, recall, let us determine the intensity maxima and minima. I is equal to I 0 into cos square delta by 2, and the intensity maxima are given by phase differences delta is equal to 2 pi by lambda into R 2 minus R 1 equal to plus minus n times 2 pi, where n is equal to 0, 1, 2 etc. That is the path difference. So, we can see here 2 pi cancels, lambda goes here, and we have R 2 minus R 1 is equal to plus minus n lambda. N is called the order of the maxima. Similarly, the intensity minima are given by phase difference is equal to plus minus n plus half into 2 pi. So, we can put numbers n here. So, n equal to 0, 1, 2. So, if you put n equal to 0, we get pi, delta equal to pi. If we put n is equal to 1, so this is 3 by 2, 2 cancel. So, it is 3 pi and so on. So, with n is equal to 0, 1, 2, etc. And or the path difference R 2 minus R 1 is equal to plus minus n plus half lambda. The plus sign gives position of maxima on one side of the point delta is equal to 0. So, let me keep the diagram here. At the point O, R 1 will be equal to R 2 and therefore, delta is equal to 0, path difference is equal to 0. On one side the path difference is positive and on the other side the path difference is negative, because when R 2 for a point P here, R 2 will be smaller than R 1 and therefore, path difference is negative. And accordingly, we will have the phase difference negative on this side, phase difference positive on this side. Therefore, the conditions here, the plus sign in this expression here gives position of maxima on one side of the point delta is equal to 0, while the negative sign gives on the other side of the point O is equal to of the point O or delta is equal to 0. So, let us see the position of maxima and minima. We have seen the condition for maxima and minima. Now, let us see the position x for maxima and minima. So, position of maxima and minima. So, at the point O, so let us see the diagram here. At the point O, which is on the perpendicular bisector here, S1O is equal to S2O, S1O is equal to S2O, means R1 is equal to R2. Therefore, we have the phase difference equal to 0, that corresponds to n equal to 0, and this is a point of maximum intensity, because n is equal to 0 corresponds to 0 phase difference and that is a point of maximum intensity and it is called the 0th order maxima. We will get maxima and minima here, because we have already seen the intensity varies with the delta and delta is sinusoidally, that is the cos square variation, and delta is proportional to x or x is proportional to delta, and therefore, we have the same cos square variation with x. And at the point O, we have phase difference is equal to 0 and that corresponds to the condition here. So, the phase difference is equal to 0, means n is equal to 0, we have the condition for maxima and therefore, this point will be maximum. In fact, this is called the central maxima, it is the central maxima. Central maxima is defined as the point at which the path difference is 0. It is not, it may not be at the point O always, depending on the correct definition would be the central maxima corresponds to the point of 0 phase difference or 0 path difference. We will see later on that due to insertion of a glass slide or due to some phase change, the central maxima may not be at O, it may appear at a different point. Therefore, the central maxima is defined as the point at which the phase difference is 0. Now, the next maxima, so here the next maxima occurs when R 2 minus R 1 is equal to n lambda, that is 1 lambda, which means R 2 minus R 1 we have already derived the expression for the. So, we have just now derived the expression that R 2 minus R 1 is equal to x d by d, and when R 2 minus R 1 becomes equal to lambda, that is n equal to 1, we call that as x 1. The position of the first maxima is x 1 d by d is equal to lambda, or the position of the first order maxima x 1 is equal to d by d into lambda. Exactly in general for different values of n. So, x n, the position of the nth order maxima is given by x n is equal to n times d by d into lambda, and therefore, we can determine the separation between adjacent maxima, and therefore, the separation between adjacent maxima is x n plus 1 minus x n, which is denoted as beta. Beta is equal to n plus 1 d by d lambda minus n d by d lambda equal to d by d into lambda. We will discuss about this beta in subsequently, but note that the beta is proportional to d and it is inversely proportional to the small d, which means at any given wavelength, and therefore, the separation between the maxima will be large if d is small, and the separation will again be large if d is large. That is why, although it is multiplied by lambda, which is a very small number. So, this is maybe 600 nanometer, 500 nanometer, which is a very small number. However, if it is multiplied by a large ratio, that is by making d small and d large, we can have significant separation beta. We will discuss this with more numbers, but let me take a typical number here. D is equal to 100 centimeter, d small d is equal to 0.3 millimeter, and lambda is equal to 600 nanometer. This is about the orange color, orange light. Then we can calculate beta, which is the separation between adjacent maxima, as 2 millimeter, which can be seen by eye because it is a 2 millimeter separate, the intensity peaks are separated by 2 millimeter. So, similarly, the position of minima are given by R2 minus R1 is equal to x m by d. So, now instead of n I have used m because this is for minima, m standing for minima, positions of minima, x m by d is equal to x m into d by d is equal to plus minus m plus half lambda. You could as well use n, but I have just used m to make a difference between the intensity maxima, positions of the maxima and minima. So, m is equal to 0, 1, 2, etc. Thus, x m, that is the position of the maxima minima, is given by m plus half d by d into lambda. There is no central minima because the central, the 0th order is maxima, as we know, as we have just seen, and therefore, when m is equal to 0, there is a path difference which is lambda by 2, and therefore, m equal to 0 gives position of the first minima, m equal to 1 gives the position of the second minima, and so on. So, in this formula we have m is the position of the minima, but m equal to 0 gives position of the first minima, and so on. Now, we have determined, so what we have determined so far is the intensity distribution on the x axis. So, on the x axis we have a cos square intensity variation at different points on the x axis with maxima at the point O and maxima and minima on both sides of the point O. But we want to see in general what would be the intensity distribution on the entire screen. So, this is okay on the x axis we have determined. How to determine the intensity distribution on the screen? So, we have to consider an arbitrary point q anywhere on the xy plane, and therefore, let us do that and find out what is the intensity distribution on the plane. Now, we have got intensity distribution on the line along the x axis, but now we want to determine the intensity distribution on the whole screen. So, let us consider an arbitrary point q. So, let me show the diagram again for, so here, so this is the Young's double hole interference experimental setup, but now instead of taking a point on the x axis here, I am taking an arbitrary point q. So, S1, S2, a point q here. So, the point q will have coordinate x, y and 0. The point S1, the coordinate of point 1, please see that it is x, y, z. So, the O is x equal to 0, y equal to 0 and z equal to 0. Therefore, the corresponding coordinates of S1 and S2 are S1 d by 2 as before, because it is the total separation is d. So, it is d by 2 here, and minus d, this is in the reverse direction, therefore, it is minus d, the separation is d, therefore, the coordinate z coordinate is minus d. Similarly, S2 is minus d by 2 because it is in the lower x axis, in the x axis below 0, and therefore, the coordinate here is minus d by 2, 0 and minus d. And the path difference, we have to determine the path difference R2 minus R1, which is shown here S2q minus S1q. So, once we know the coordinates of the points, we know how to determine the distance between the 2 points. So, we will determine the path difference. So, let us determine the path difference at any arbitrary point q. So, here, so the path difference at the point q, so let us here. So, is S2q minus S1q, let us call it as delta, say delta is given by this one. So, here, so this is S2q is x, so it is x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square, if the 2 points have coordinates x1 y1 z1 and x2 y2 z2. So, that is the formula which has been used here. So, we have x plus d by 2 the whole square plus y square plus d square, because although it is minus d, but it is square, therefore, it is d square is equal to the power half. So, this is S2q and this is S1q. So, S2q minus S1q is equal to delta. So, we take this to the other side and write and square it, so that we have this x plus d by 2 whole square plus y square plus d square, we have squared this term, this has gone to the other side, is equal to delta plus this to the power half and whole square. This can be simplified. So, I would not derive the simplification steps, we can easily simplify this and to get an expression that d square minus delta square into x square minus delta square into y square is equal to this term here. For a fixed value of delta, that is delta is what is delta is the path difference. For a fixed value of delta, that is if you choose a point q, then it has a path difference delta. So, for a fixed value of delta, the above equation is of the form. So, we can divide by this on this side, then we will have it is of the form x square by a square minus y square by b square is simply delta square divided by all of this. So, delta square cancels. So, this in the denominator is b square is equal to 1. So, this is an equation of a parabola. Note that these are positive constant. See, d is much larger than delta. Delta takes values of lambda, 2 lambda, 3 lambda, a few lambdas, and d takes values which are of the order of millimeter or 0.2 millimeter, 0.5 millimeter. This is of the order of micrometer, typical values of d. So, we can put what is d? D is, so d is, I have already said that this is typically from this to 1 mm. What is delta? Delta is the path difference. So, we are interested in finding the fringes where path difference can be lambda, 2 lambda, 3 lambda, of course, intermediate values also, but they are a few lambdas. So, few lambda, this is few mm, lambda is 600 nanometer, which implies it is 0.6 micrometer. So, few lambda is therefore of the order of micrometers, and here it is of the order of millimeter, d is of the order of millimeter, that is a factor of 10 power 3. So, micrometer is 10 power minus 6, millimeter is 10 power minus 3 meters, and therefore, d is much larger than delta, and therefore, this quantity here d square minus delta square here is always a positive quantity, and therefore, x square by a square a positive quantity minus y square by b square, which is the equation of a hyperbola where a and b are constant. For different values of delta, different if we put delta is a constant, but if I take different values of delta, we get different hyperbolae, that is the locus of all points with the constant path difference are hyperbolae. So, let me explain this. So, this is the equation of an hyperbola for a given value of delta, because this is of this form. A and B are constants, fixed constants for a fixed value of delta, because D is fixed for the given experimental setup, capital D, the separation is also fixed. It is only delta which will vary from point to point as we change the point Q. But for a fixed value of delta, if we assume delta is equal to lambda, for example, delta is equal to lambda, then this is a fixed constant and we have a particular hyperbola. So, let me draw this hyperbola here. So, this is the x axis and this is the y axis. So, we will have for one particular value of delta, we will have hyperbola like this. So, this is for a particular value of delta. Now, delta 1 let me call. If I take a different value of delta, then I will get another curve here. So, delta. So, depending on the value of delta, we will get a family of hyperbolae here. So, what we will have? So, this is delta, delta 2, delta 3. For different values of delta, we will get different hyperbolae. For example, if delta 1 is equal to lambda, then we know that the path difference lambda would correspond to a bright point. It is a bright point or intensity maxima, and therefore, if for delta 1 equal to lambda, if this were the curve, then it will simply tell that this is a locus of all points which are bright points. So, this is bright points. So, all the points along this are bright, because delta 1 is equal to lambda, path difference is equal to lambda. If this curve here, so delta 2 here is equal to, let us say 3 by 2 lambda, 3 by 2 lambda, then these points will correspond to dark points. This is the locus of all dark points, this is the locus of all bright points. In other words, what we will see are bright and dark hyperbolae. Alternatively, because delta will continuously increase in this direction, therefore, alternatively we will get bright and dark hyperbolae, and these are nothing but the fringes. So, what I have shown here is therefore, so let me put again, for different values of delta we get different hyperbolae. The locus of all points with constant path differences are hyperbolae. This means that we get bright and dark fringes. So, let me show you some fringe system here. So, interference fringes. So, let us discuss the interference fringes. As I have discussed, if delta is equal to n lambda, then the hyperbola would comprise of all points. Whenever delta is an integral multiple of lambda, then the hyperbola, that particular hyperbola would comprise of all points with the intensity maxima. And if delta is n plus half lambda, then that hyperbola would comprise of all points with intensity minima. This implies we will see alternate bright and dark hyperbolae on a screen. These are called the interference fringes. So, it is the first time we are introducing interference fringes, and the pattern on the screen is called a fringe pattern. So, I had shown earlier that I did not show a hyperbolic pattern here, but so what we have is a linear fringe pattern. So, we can see alternately bright and dark fringes. I will show a hyperbolic fringe pattern at a later time. So, this it could be. Now, if the locus of all points with a constant path difference, in this case the case that I had discussed, it happens to be hyperbolae, constant path difference, but in a particular setup, if the locus of all the points with a constant path difference happens to be circles, then we will get circular fringes, and we will get circular fringes like this. So, the circular fringes that I had showed you here is because the locus of constant path difference are circles in this case, and if the bright fringes correspond to n lambda, whenever path difference is n lambda, and the dark fringes correspond to path difference n plus half lambda. So, that is how we get the fringe system in a interference setup. So, we have discussed the formation of interference fringes here, and now we come back to the interference fringes in the Young's setup, in the Young's experimental setup. So, this formula we have derived, we have just now showed that, let me put this here. So, we just now showed this, that d square. So, this is the equation of the hyperbola, interference fringes in Young's experiment. Now, or x is equal to, so we take this to the other side, and then we will have delta square multiplied by this, and then divide by this here and take square root to get x is equal to delta divided by this into this. In practice, I have already discussed that y is much smaller than d, y is few millimeter, y is the distance on the screen. So, this is the screen xy axis, and we are talking of this area which has dimensions of few millimeters to few centimeters only, and therefore, whereas d is of the order of 100 centimeters, and therefore, y is much smaller than d, y a few millimeter to centimeter, and d is of the order of 100 centimeter, and therefore, y square can be neglected in comparison to d square in the case of the Young's experimental arrangement. So, we had just seen that I had showed you a practical arrangement where the distances are very large. So, we can see here d is much larger compared to x and y, the x and y which are here on the screen is much smaller compared to this, and therefore, we can neglect y square compared to this d square. This is millimeter square, this is 100 centimeter square, and therefore, we can write x is equal to approximately equal to, is a very good approximation, but approximately equal to this. Now, for a given delta, for a fixed value of delta, right hand side is a constant, right hand side is a constant. What it means is that that is x is equal to constant for each fixed value of delta. This implies locus of constant path difference are straight lines parallel to the y axis, x equal to constant, x equal to constant are straight lines, unlike this hyperbole. This is hyperbola is the exact solution, but if y x and y are much smaller than d, then this will turn out to be a straight line. So, x equal to constant for each fixed value of delta. This is a very valid approximation. Here there is no approximation, but here there is a valid approximation, and these therefore, this leads to straight line interference fringes. So, the interference fringes in Young's experiment are straight line interference fringes. So, that is what I had shown earlier, that we get straight line interference fringes. So, the fringe system would look like this. So, along the x axis, x equal to constant, the locus of constant path difference are x equal to constant, they are straight lines parallel to the y axis or perpendicular to the x axis. So, this is the type of fringe system that we will see, and the separation between these bright lines is called the fringe width beta. Beta is the separation between the bright points. Now, I have shown here in this diagram the point P which is on the x axis and an arbitrary point Q here. If P is a bright line, bright point or intensity maxima, then all along that line intensity will be maximum, because we have just seen that x equal to constant corresponds to the locus of all points with bright or dark depending on the delta value. Therefore, if we determine the separation between the intensity maxima along the x axis, then it is nothing but the fringe width, that is the separation between the two bright fringes. The separation between two bright fringes is called the fringe width, which is also nothing but the separation between two adjacent maxima. So, this is what we had discussed earlier, and here I come to the last part, that is fringe width. The separation between the adjacent bright or dark fringes is called the fringe width. Recall that beta is equal to here d by d into lambda. This was the separation between maxima on the x axis. Just now we have derived that x is equal to this, expression for x is this, but I have explained that delta, the path difference delta is much smaller than d, which is much smaller than d, and therefore, this term here, this delta can be neglected with respect to this d, but this d itself is negligible. The d square here is negligible compared to the d square here. Again, let me repeat that this is of the order of 100 centimeters. So, 100 centimeters square, whereas this is of the order of 1 millimeter square, extremely small compared to this, and therefore, this term can be neglected. And similarly, with respect to d, delta is negligible, almost 1000 times smaller, and therefore, we can neglect this, which means we get x is equal to delta into d by d. X is equal to delta into d by d. For delta is equal to 0, that is 0 path difference, we get the position x equal to 0, which is a constant. X equal to constant gives us the fringes. The constant in this case is 0. For delta is equal to 0, x is equal to 0, which is equal to constant. The fringe is given by x equal to constant and x equal to value, the value of x being 0, which means it is the y axis is the locus of all bright points, that is the central fringe. Y axis is the locus of all bright points when the path difference is 0, delta is equal to 0, path difference is 0, and that is called the central fringe. So, in this case, y axis, the bright fringe along the y axis is the central fringe. If delta is equal to lambda, substitute in this delta is equal to lambda, then we get x1, the position of the next bright fringe, as lambda into d by d. If delta is equal to 2 lambda, path difference equal to n times lambda, we get the position x2 is equal to 2 lambda into d by d, that is the second bright fringe, and therefore, the fringe width is given by x2 minus x1 is equal to lambda into d by d, as before. So, this is the fringe width, that this is the difference between the maxima on the x axis which we had determined earlier, but it is the same difference that we get for the fringe width. So, to determine the fringe width, one can as well consider the points along the x axis. We will put some numbers and discuss this more carefully in the next lecture. Thank you.